ఓకే.
ఒక 2 minutes వెయిట్ చేద్దాం. మ్యామ్ ఒకసారి చెక్ చేసి మళ్ళీ జాయిన్ అవుతాం మ్యామ్. ఒకసారి ఎందుకైనా మంచిది. అదే అనదర్ ఏమైనా క్లాసెస్ నడుస్తున్నాయేమో. హలో మ్యామ్.
Dear students, every day let us do one theorem revision. So we are I want to say important theorems I am planning to revise once again. Continuous functions. Because last class I have explained what is a open base, what is a open subbase, and what is a topology. What do you mean by topology? A collection of subsets of a non-empty set X is called a topology if empty set belongs to X and X belongs to X. And intersection of any collection. You have empty set belongs to tau and X belongs to tau. If A and B are any two sets of tau, their intersection is again in tau. I belongs to I is a subset of tau means that means union of finite collection of subsets of X is again in tau. So now let us talk about continuous functions. I will be going to revise in every class one theorem because this topology is a little bit difficult concept. See here, suppose you have X D1 and Y D2 be two metric spaces where D1 and D2 are metrics on X and Y. And F from X to Y be any function. Be any function. And X naught belongs to X. Then we say that F is continuous at X naught if we have for each epsilon greater than 0, there exists a delta greater than 0 such that d1 of x comma x naught is less than delta implies d2 of f of x comma f of y is less than epsilon. Is less than epsilon. So it is equivalent to say that for every open sphere S epsilon of f of x naught centered on f of x naught, there exists open sphere, S delta x naught such that you have f of f delta x naught is a subset of S epsilon f of x naught. Both are equivalent. That means in terms of metric modulus, mod x minus x naught less than delta implies for each epsilon greater than 0, there exists a delta greater than 0 such that whenever mod x minus x naught less than delta, we have mod f of x minus f of x naught is less than epsilon. Then we say that the function is continuous. Okay, so let us see one example. Just I want to say this as example. See here, consider the function. Hello, anybody join? Okay.
Yes, ma'am.
Yeah. Suppose let us do revision. Daily one theorem, one old theorem I will explain, and then again I will start one new concept. Is it okay?
Okay, ma'am.
Suppose you have f of x is equal to 3x plus 2. You are asked to prove that this function f of x is equal to 3x plus 2 is continuous on R. If this is continuous on R, what you have to prove? Suppose you take any point x naught, arbitrary point x naught. Consider f of x.
Madam, page number, please.
General example I am giving, Amma. Okay.
Okay. Okay, ma'am.
Just I am taking one f of x equal to 3x plus 2 is continuous on R. Now, for any x naught belongs to x, consider mod f of x minus f of x naught 3x plus 2 minus 3x naught minus 2. 2 will get cancelled. You get modulus of 3x minus 3x naught, or this is 3 into mod x minus x naught. They may ask you for 5 marks or 6 marks. Part B, prove that this function is continuous. So what you have to do, see here, when now you have mod f of x minus f of x naught will be less than epsilon if and only if 3 into mod x minus x naught is less than epsilon, isn't it or not? Now this is if and only if mod x minus x naught is less than epsilon by 3. That means you choose a delta. You choose delta is epsilon by 3. Or if you choose a delta which is epsilon by 3, then you get whenever mod x minus x naught is less than delta, you will get mod f of x minus f of x naught is less than epsilon. Therefore, the function f is continuous on R since x naught is an arbitrary point. Since x naught is an arbitrary point. Now, based on this continuous, definitely you will get one question for 10 marks. I told you f is continuous. F is continuous. Page number 31, theorem 4.3.2. F is continuous if and only if xn converges to x naught implies f of xn converges to f of x naught. This already we can know. Whenever f is continuous, you will get, suppose f is continuous. F is continuous at a point x naught, which implies there exists delta greater than 0 such that d2 of f of x comma f of x naught is less than epsilon whenever d1 of x comma x naught less than delta. So you take here x equal to x naught, xn. If you take x equal to xn, you get d1 of xn comma x naught less than delta. So whenever you have d1 of x comma x naught less than delta, d2 of f of x comma f of x naught is less than epsilon. Now for one x equal to xn, that means that is the nth term. d1 of xn comma x naught less than delta implies d2 of f of xn comma f of x naught is less than epsilon. That means you have xn converges to x naught implies f of xn converges to f of x naught. So this is the first part. Whenever f is continuous, f is continuous if and only if xn converges to x naught implies f of xn converges to f of x naught. First, what I am proving, and whenever there is if and only if condition, there you have what you have to prove. You have to prove the theorem in two parts. First, suppose f is continuous, and whenever xn, what is required to prove, you focus only on two things. What is given, what you have to prove. Given that f is continuous. So what we have to prove, whenever xn converges to x naught, we have to prove f of xn converges to f of x naught. What do you mean by xn converges to x naught? You have, for given epsilon greater than 0 or for given delta greater than 0, there exists a positive integer m belongs to z plus such that d of xn comma x naught less than delta. Am I right? So we have d1 of c given f of x is continuous or f is continuous at x naught. Whenever f is continuous at x naught, you have d1 of x comma x naught less than delta implies d2 of f of x comma f of xn converges f of x naught is less than epsilon. So what do you mean by d of xn comma x naught is less than delta? You have d2 of f of xn comma f of x naught is less than epsilon. So whenever xn converges to x naught, you have f of xn converges to f of x naught. Conversely, suppose whenever xn converges to x naught, suppose f of xn converges to f of x naught, then what we have to prove? F is said to be continuous. So see here, if possible, what will happen if f is not continuous? So what is happening when f is not continuous? You will have d of x naught, d of x comma x naught less than delta, which implies d2 of f of xn comma f of x naught will be greater than or equal to epsilon when f is not continuous. Conversely, what we supposed? Whenever xn converges to x naught, we supposed that f of xn converges to f of x naught. What do you mean? That is d1 of x comma x naught less than delta implies d2 of f of xn converges to f of x naught is greater than epsilon if f is not continuous. Given that whenever xn converges to x naught, we have f of xn converges to f of x naught. What is required to prove? We prove that f is continuous at x naught. We will see what will happen if f is not continuous at x naught. If f is not continuous at x naught, you will have d2 of f of xn comma f of x naught greater than or equal to epsilon. That means you will get that means, what do you mean by this? If your f of xn does not converges to f of x naught, which is a contradiction to your assumption. Therefore, you have xn converges to x naught implies f of xn converges to f of x naught. Then f must be continuous. Students, are you following? Are you listening? Yes. Yeah. I understood. Now, yeah. So this is about continuous. Now let us come to new chapter called, now today we are planning to do separation axioms. Now next topic is, generally every class I will repeat the old theorem and again new concepts and old concepts. Now separation. What do you mean by separation? I tell you, we have a college like this. In this, just let us have classes. You have a school of sciences. You have school of informatics. You have school of commerce. Okay. Now, this is the college. Some you take Ambedkar University only. Now, suppose this is a student X. Here is a student Y. Now, you have X belongs to university, Y also belongs to Ambedkar University. But you have x not equal to y. Isn't it or not? You have x not equal to y. Suppose if you have this is set G and this is set H, you have x belongs to G, x belongs to H. Okay? But G and H are open sets such that, see, you are separating the points. Isn't it or not? X and Y can be separated by the sets G and H. You have X is a student of School of Sciences, Y is a student of School of Informatics. Both of them belongs to university, but they do not belong to the same school. They do not belong to the same school. That is why your points X and Y are separated. So this concept, we are introducing separation in terms of different definitions. We are going to talk about T1 spaces, T2 spaces, Hausdorff spaces, and all. This is called separation. Separation is a very important concept in topology, and this is also in real analysis. And then further, we are going to prove theorems on this. That's what. So yeah, what I am saying, you have a set G. You have a set H. Your X is there, Y is there. So that is, there are some common points. Okay, and there are some common points. But here, there are no common points. Now here, see, a topological space X is called a T1 space. A T1 space if for X not equal to Y, there exists open sets G and H such that X belongs to G minus H and Y belongs to H minus G. See, this is what you call, this set is called G and this is G minus H. This is H minus G. Sometimes there are, see, suppose if you take School of Sciences and School of Informatics, these two subjects may have one common paper as mathematics. Okay, one common paper as mathematics that will come under this intersection. Only whenever they are, but it is not always true for all the sets. So here we say that a topological space X is called a T1 space if a topological space X is called a T1 space if for X not equal to Y, there exists two sets or two open sets G and H such that X belongs to G minus H and Y belongs to H minus G. Okay. Now see here, generally, if you are defining a topological space or a T1 space, see, let X be a topological space. Theorem. Let capital X be a topological space. Then capital X is a T1 space if and only if the singleton sets X the singleton sets X is closed for every X belongs to X. That means if X is closed, it means its X complement is open. X complement is open. So here, suppose X is a T1 space. If X is a T1 space, then what you have to prove? We prove that X complement, that is capital X minus singleton X, is open. Okay, if it is open, hence you will have singleton set X is closed. So see here, suppose you take one Y belongs to X minus singleton X, then we have X not equal to Y and because T1 is because X is a T1 space, there exists open sets G comma H such that you have X belongs to G minus H and Y belongs to H minus G. Y belongs to H minus G. So this implies you have Y belongs to H, but H is a subset of, tell me, what is H? H is a subset of X minus singleton X. That means X minus singleton X is subset of some open set. Means you have X minus singleton X is open. Hence, singleton X is closed. This is one 6 marks question for part B. Students, all of you understood about T1 space. T1 space means separation. You take 2 classes and both one BCom class and one B.Sc class. One BCom class and B.Sc. If you take one student from BCom class and one student from B.Sc class, even though those students belongs to same college, but they belongs to different sections. So that is nothing but we are separating the 2 students with the help of their subjects or with the help of their programs. Okay, so here that's what you mean by T1 space. When we say that a topological space X is a T1 space, if for X not equal to Y, there exists 2 open sets G and H such that X belongs to G complement, Y belongs to H complement, or you can say X belongs to G, but X does not belongs to H. Y belongs to H, but Y does not belongs to G. All of you know definition of A minus B. Now, immediately after defining this separation concept, what I want to prove is whenever X is a topological space, when a topological space will become a T1 space, a topological space becomes a T1 space if and only if the singleton set X is closed. What do you mean by singleton X is closed? Capital X minus singleton X is open. So first suppose X is a T1 space. Always I have been telling you, you focus on 2 concepts. One is what is given and what you have to prove. If you have a clarity on these 2 concepts, definitely you will get how to prove. Suppose X is a T1 space. If X is a T1 space, we prove that singleton X is closed. So if you want to prove singleton X is closed, we prove capital X minus singleton X is open. When you say that your set is an open set, if it is a subset of some open set. Now take Y belongs to capital X minus singleton X. That means singleton X complement. Then definitely you have X not equal to Y. What is the assumption on our X? X is a T1 space. So because X is a T1 space, you have there exists open sets G comma H such that X belongs to G minus H and Y belongs to H minus G. So what do you mean by this? You have Y belongs to H anukunna. So Y belongs to H and Y belongs to capital X minus singleton X. So both are the subsets. So you have capital X minus singleton X is open. Hence singleton X is closed. That means what we have proved, whenever X is a T1 space, the then singleton X is closed. Now, as a converse part, conversely, suppose singleton X is a closed set. Then what we have to prove? We prove X is a T1 space. X is a T1 space. So what do you mean by this? See, what you have to prove if you want to prove X is a T1 space, take two distinct points in X. Let X not equal to Y belongs to X. Now take G is equal to capital X minus Y, and H is this you have to choose. H is equal to capital X minus singleton X. Then definitely what you have both, because you have singleton X is closed, because we are saying that X is a T1 space, and if you have X comma Y belongs to X, implies singleton X is closed, singleton Y is closed. Then you have G is equal to capital X minus singleton Y, H is equal to capital X minus singleton X. So you have open sets G and H such that X does not belong to Y, implies X belongs to G, but X does not belong to H. And you have Y belongs to H, but Y does not belong to G. So you have T1 is the X is a T1 space. Students, is this concept clear? Hello? Are you following?
Yes, ma'am.
Yes, ma'am.
So this is one important theorem. See, I told you now when I took offline classes, you can prepare the first half perfectly, and from separation and all, you learn these concepts just. Otherwise, you cannot learn further concepts in function analysis. Second year concepts, it may be tough without the knowledge of this separation. Separation you have to learn. Or we can say that, from this we can say that a topological space X is a T1 space. X is a T1 space if and only if every finite set or finite subset of capital X is closed. So if you want to give an example for T1 space, I told you, Nama, you can take any two students from different programs, can be separated by two different classes. Or you can say that a metric space, if they ask for example, you give this example. A metric space, capital X is a T1 space. A metric space capital X is a T1 space. Why? Because you can say, let X not equal to Y belongs to X. Then what will happen? D of XY, because both are not elements of X, definitely the distance between them will be greater than 0. D of XY is greater than 0. Take two open spheres, SRX centered at X. H you can take it as S or Y. Then definitely G is an open set. H is, we proved every open sphere is an open set. Every open sphere is an open set. So you can have X belongs to G minus H and Y belongs to H minus G. Therefore, every metric space is a T1 space. Students, do you remember I explained about cofinite topology? Cofinite topology is like this only, x minus a, x minus a, x minus b. We know about cofinite topology. I will once again, I will remind you. Let x be any non-empty set with together with the topology. Tau is equal to G is a subset of X such that you have either G is empty set or X minus G is finite. G is empty set or X minus G is finite. We proved that this tau is a topology. We proved that this tau is a topology. So X together with this topology is a T1 space. Because you have, see, because for any X belongs to X, you have capital X minus singleton X is open. Therefore, singleton X is closed. So hence a cofinite topological space is a T1 space. And the next one, just we are studying the consequences. We are studying the consequences of after definition of a topological space. We know that the first one is any subspace of a T1 space is a T1 space. Any subspace of a T1 space is a T1 space. At the same time, you have the product of any class of T1 space is a T1 space. Is a T1 space. The product of any class of T1 space is a T1 space. Suppose proof. All these, just to read it and leave it. From this part you learn. I told you as before, Urysohn's embedding theorem, T's extension theorem, Urysohn's lemma. These three theorems are very important. These three you learn and leave it. Because as I have to teach each and everything, I'm giving you knowledge about each and every concept of the topology, whichever is there in your syllabus. But if you want to get full marks, it is enough if you learn the first 8 units. First 8 units only, very, very important. You will be able to definitely write 4 questions. And last theorem, you learn T's extension theorem, Urysohn's embedding theorem, and Urysohn's lemma. Let Y be a subspace of, let Y be a subspace of T1 space. Let capital Y be a subspace of T1 space. X. Suppose you take Y belongs to Y. You have Y is a subset of X, means Y belongs to X also. Am I right? Whenever Y belongs to X, you have Y is closed. Singleton sets are closed sets. Singleton sets are closed sets. Now, how you write singleton Y? You can write it as capital Y intersection Y, which implies you can write like this, because you have A intersection X is A only. So Y intersection Y is Y only. So you have Y is closed. Y is closed in Y also. Therefore, Y is a T1 space. Therefore, Y is a T1 space. Next, for 6 marks, the product of any class of T1 spaces is a T1 space. Let X alpha belongs to delta be a class of T1 space, and capital X is product of X alpha. Alpha belongs to delta. Okay, together with product topology. Now let X comma Y belongs to X and X not equal to Y. X not equal to Y means what will happen? There exists some alpha naught such that X alpha naught not equal to Y of alpha naught both belongs to X alpha naught, because you have X alpha 1, X alpha 2, these are all T1 spaces. Now what do you mean by this? You have X alpha naught is a T1 space. So there exists G alpha naught and H alpha naught in X alpha naught, such that because it is a T1 space. And what do you mean by T1 space? Any 2 points are separated by 2 open sets. Any 2 points are separated by 2 open sets. So there exists G alpha naught, H alpha naught such that you have X alpha naught belongs to G alpha naught minus H alpha naught, and Y alpha naught belongs to H alpha naught minus G alpha naught. So you take projection P alpha naught from X to X alpha naught. Then you will get G, you can take it as P alpha naught inverse of G alpha naught. And capital H, you can take it as P alpha naught inverse of H alpha naught. So you have G and H are, then if you take like that, then G comma H are open in X and X belongs to G minus H, Y belongs to H minus G. So you have then capital X, which is equal to capital X is equal to pi alpha belongs to delta X alpha is a T1 space. So product of T1 spaces is T1 space. Product of T1 spaces is a T1 space, and any subspace of T1 space is a T1 space. Now let us define T2 space. This T2 space is also known as Hausdorff space or Hausdorff space because it is invented by mathematician Hausdorff. I tell you the difference. See here, in T1 space, 2 points X and Y are separated by distinct open sets. But in T2 space, what is happening is any 2 points are separated by 2 disjoint sets. There we don't talk about G and H, whether they are disjoint or not. But here in T2 space, 2 points are separated by 2 disjoint open sets. So how you define a Hausdorff space, a topological space? A topological space, X is called a Hausdorff space or a T2 space, Hausdorff space or a T2 space. If for any x not equal to y belongs to x, there exists open sets G, H such that x belongs to G, y belongs to H, and G intersection H is empty set. That is, there exist two disjoint open sets. When do you say that two sets are disjoint? If they have no element in common. If they don't have any element in common, then we say that the two sets are disjoint. A topological space X is called a Hausdorff space or a T2 space if for any x not equal to y belongs to any two distinct points are separated by two disjoint sets. Okay. So you have every Hausdorff space is a T1 space, but converse need not be true. All T1 spaces need not be Hausdorff spaces. Students, any doubts? You can ask me questions because last 5 minutes are there. No, you can ask the questions. See, let us see some examples of students. Yesterday, anybody took my class?
No, madam.
Oh, okay. So actually, yesterday class I will take today at 3 to 4. Okay.
Okay, madam.
In algebra class, algebra class I will take. Okay.
Okay, madam.
1 minute. Some chart are there. Okay. Chart. Now let us see some examples. You give this example. Hausdorff space also give an example as a metric space. Every metric space is a Hausdorff space. Every metric space is a Hausdorff space. Why? Because see, suppose x comma y belongs to x, where x is a metric space with respect to metric D. Then x not equal to y and definite x not equal to y. Then only you will have distance between x comma y is positive. Now you can take open set G is equal to some SRX, H is equal to some SRY. So then you have G is an open set containing X, and H is a open set containing Y. G is an open set containing X, H is an open set containing Y, and also you have, because X not equal to Y, you have G intersection H is empty set. Okay. Why? Because if some Z, already I took X and Y, now I'm taking Z. Suppose if Z belongs to G intersection H, then you have Z belongs to G and Z belongs to H. Means you have Z belongs to R, mana convenient kosam R by 2 తీసుకోండి. Z belongs to S R by 2X and Z belongs to S R by 2Y. So what will happen? This implies D of X comma Z is less than R by 2. Here, D of Z comma Y is less than R by 2, which implies D of X comma Y, which is less than or equal to D of XZ plus D of ZY, which is less than R by 2 plus R by 2, which is R. Okay, and so you take R is some D of XY. You get D of XY less than or equal to D of XY, strictly less than D of XY. So this is a contradiction. Therefore, you have G intersection H is empty set. So 2 points X and Y are separated by 2 points X and Y are separated by 2 disjoint open sets. Any doubt in T1 space or Hausdorff space? Did you get the difference between a T1 space and a Hausdorff space? There 2 points are separated by 2 open sets. In Hausdorff space also, 2 points are separated by disjoint open sets. There you won't mention disjoint, but here we mention disjoint open sets. So in the afternoon class, I will do 2 or 3 theorems related to Hausdorff spaces. And one theorem, one old theorem I will teach you. Old syllabus. Old means, I mean for the before chapters, so that a revision will be for you, a revision for you. Any questions? You are most welcome. Doubts?
Ma'am, once again explain T2 space, please.
T2 space, yeah. What do you mean by T2 space is? A topological space is called a T2 space or a Hausdorff space for any distinct points are separated by disjoint open sets. That is, for any X comma Y belongs to X, where X not equal to Y, means X and Y are 2 distinct points. There exists open sets G and H such that X belongs to G, Y belongs to H, and G intersection H is empty. I will tell you how. That means this is X, this is G, this is H. Here you have X, here you have Y. This is the set G, H. Got my point, student? Here, X not equal to Y, and you have X belongs to G, Y belongs to H, such that G intersection H is empty set. They have no common point. Whereas in T1 space also same like this. But how we are saying G and H need not be disjoint. This is H, this is G, H. This is G minus H. This is H minus G. You have X belongs to G minus H, Y belongs to H minus G. Got my point? Where G and H are open sets. Here definitely G and H has no common points, but here you can have G and H common points. Did you find the difference between T1 space and Hausdorff space?
Okay, madam. Understood.
Understood, ma'am.
Yeah, okay. Shall I leave the class?
Okay, ma'am.
Okay,
Okay,
ma'am. Thank
madam.
you.
Yeah,
Thank you, ma'am.
welcome. When next I will take at 3 o'clock today. Okay.
Okay, madam.